Thank you. So I'm going to speak about learning to see in VR. Extraretinal cues improve accuracy of 3D motion perception in virtual reality environments. Typically, we're successful when we navigate busy 3D environments in our daily lives, and we have an intuitive sense that our vision is accurate while we're doing so. However, laboratory studies suggest that people are actually poor at 3D motion perception. But, to give you a few examples, in one series of studies, participants were asked to estimate the direction of objects that were approaching in the world. And so data are typically presented with the presented direction of the stimulus on the x-axis, and then we look at their report on the y-axis. Now what we can see is that when an object is directly approaching a participant, they report it as directly approaching, and they get this correct. However, when the object is moving more off to the side from the participant, such as in this case, what we find is that the data point is no longer on the positive diagonal, and in fact it's consistent with a more lateral motion direction. And so the implication of this is that objects that are moving towards participants are potentially perceived as moving more off to the side. In related work, participants again are asked to judge the direction of objects moving in the world. However, this time the objects are not strictly approaching, but they're also receding. So once again, we plot the presented direction of the object moving in the world on the x-axis and their reported direction on the y. And when we look at our raw data set using this task, what we find is an interesting pattern of results like this. So there are three features to this data set. The first is that a good chunk of data points fall along the positive diagonal, and this is consistent with participants doing the right thing. So for example, when an object is approaching, participants report the object as approaching. There's also a negative diagonal in this data set, and this is consistent with participants misreporting or reversing the motion and depth direction of the stimulus. So once again, for example, when the object is approaching the participant, they report it as moving directly away from the participant. And again, this is somewhat problematic in the real world. If there's objects coming towards us, we don't want to be recognizing them as moving directly away. And finally, a third feature in this data set is that there's a heavy mass of data points on the lower portion of the plot. And this is consistent with a greater likelihood to report objects as receding in the world. And if anything, we would want to be more likely to report objects as approaching, again, for the sake of safety. So these results are just some of many that suggest that people are poor at 3D motion perception. And the hypothesis is that we rely on strong prior assumptions when carrying out tasks in the real world to avoid the impact of these types of errors. However, today what we're going to discuss is an alternative explanation, and that's simply that there's a strong disconnect between the laboratory viewing conditions and those that we experience in the real world. So consider for a moment the laboratory versus the real world. In general, the laboratory just simply doesn't recreate the real world viewing, and that's because participants are generally tied to a display. They view them through glasses or a stereoscope, and they only get a single viewpoint of the scene, versus the real world in which they're unrestrained and they can have multiple viewpoints of the scene. So this is where virtual reality comes in. So it provides a unique method to bridge the gap between perception of motion in the laboratory and perception of motion in the real world. So as a first step, we're going to take a developed laboratory task and move it into the VR environment and look at performance there. So we use a 3D Pong task that we've developed recently, and this is just a schematic of how the task works. So this is a top-down view of a participant. A target appears in the display and moves for 1 second along a trajectory before disappearing. Then we ask participants to make a response by adjusting a small paddle to the location that they believe would intercept the trajectory of the target they just saw. They do not receive feedback in this task. If the paddle is set to the correct position, we would code that as an interception, otherwise it's a miss. This is just a shot of the stimulus presented in the display. We have a left eye view and a right eye view. The aperture of the stimulus is 15 degrees, and we have a target that moves for 1 second, and then participants adjust the paddle position. And finally, we start by considering performance when the VR-based experiment replicates the viewing conditions of the laboratory experiment. So participants wear the Oculus DK2 in our study, and as they move their head, the display as seen on this monitor doesn't change. So we've turned off any head motion contingent updating. So we'll plot the data in the same format as we've seen previously under these head fixed conditions. And what we find is the same patterns of performance observed previously. So one consideration is that those are aggregate data, all of the raw data points. It does not consider performance over time. So it is possible that participants with repeated exposure to the task while wearing the head-mounted display, they could get better. And so when we plot performance across time by trial number, in terms of the percentage of target interceptions across participants, what we find is performance is generally poor and it's stable. It doesn't change from the first trial to the final trial. So this suggests that strapping on the VR device and having participants use this task, it replicates performance that we've seen previously in similar laboratory conditions. Again, considering real-world viewing, one thing that occurs is people make small involuntary head movements just simply when they're viewing scenes. And so if we were to have the display update according to participants' small head movements, would we see performance improve? This is unknown because we've not done this. So one thing that's important about these small head movements is that they may provide motion parallax information that participants can then use in their estimates of motion and depth. So participants carry out the task once again under the same conditions, except now we've turned on the head motion contingent updating such that when participants move their head, the scene updates right away. What's important to note is that we did not explicitly tell participants to move their head. In fact, we actually told them to keep their heads still because we asked them to fixate the central part of the stimulus while the target was moving. And when we asked participants at the end of the experiment whether they felt that they moved their head, they subjectively reported that they did in fact stay still. So this was the performance that we saw previously in the fixed condition, and now what I'll do is show you performance in the active condition when the scene updates according to any small head movements. And it doesn't change. It still looks the same. Well, what about over time? Perhaps here they're learning to do better because they have the potential to acquire additional information. Nope, it's the same. So they're the same from the beginning of the experiment at the end, and there's no additional benefit of this head motion information. So to summarize, it appears perhaps that people do have poor 3D perception in 3D environments, consistent with what we've seen so far in the literature. And we've also seen that performance does not improve with experience. So should we just quit here? Perhaps not. There's still hope. So one thing that we do know is that during development, perception requires seeing the visual consequences of one's actions. We know in kittens, if they're raised to only passively view their environment, they develop poor depth perception. So we can then ask the question, is the same required to learn to see in VR? Do people need to see the consequences of their actions? So we have participants carry out the same task, but this time we give them a feedback signal. So they view their target, They make their response, and now the target reappears at its last location, heads towards the target, and if it hits, there will be a hit sound, and if it misses, there's a miss sound, and they get to see how far off they were. Okay, so what does performance look like now? This is what we saw, once again, when feedback was not provided. Under the fixed viewing conditions when feedback is provided, lo and behold, we see a big improvement in performance. There's a much tighter clustering of data points around this positive diagonal. So what's changed? What's different? Well, when we look at performance over time in the initial data without feedback, we see no change from start to finish. But what we find with feedback is there's a rapid and significant improvement. So this is the change. Now, one question is, how does this improvement break down over our different viewing conditions when our head is fixed and there's no scene updating, and when it's active and there is scene updating? And what we can see for the fixed case is there's a tendency towards improvement over time, but it's not significant. In the active condition, however, there is a significant improvement over time. So people with experience and feedback are learning how to take advantage of information in the display with head movements. Now, one concern here is that the one potential source of improvement in performance in the active condition is that movement of the head effectively increases the resolution of the display. So in order to disentangle whether that is the improvement or whether it's truly due to the use of motion parallax information, we have a final condition in which the scene updates are lagged with respect to the participant's head movements. All other aspects of the task are the same. And so when we look at performance in this condition, what we find is that there is a significant change over time,
because I find it hard to believe that if you actually had local optical expansion in those displays, that you would get this forward and backward reversal happening much at all. So if the dots expand, or if there's a bounded contour that expands, I can't believe you'll get it. But with this sort of pure stereo motion, maybe you get it.
The dot does expand. There's all of the binocular cues. It's situated at 45 centimeters. It's a small, tiny little dot. It's about 1 degree of visual angle. I'll have to get back to you later on the actual size, but in centimeters. But this is something that we found consistently both with the shutter glasses, with the VR participants. Just they have trouble determining which direction it's going.
It's okay. Can you comment on the variability across subjects? Because your plots, obviously, they're all put together. So, for example, is it the case that some subjects only fell along diagonal and others clustered down?
These data are typical of all subjects. That's why we lump them up together. You do see some variability in terms of overall, numbers of confusions, but everyone shows this sort of X pattern.
That was a great talk, but have you compared the magnitude of the hand jitter of the experiment before and after the training? Well, probably after the training, the hand jitter is even more bigger, so they have better perception.
Just to make sure I understood your question, you're asking if we've compared the magnitude of head movements across the conditions?
Yes.
Yes, we're looking at that now, and what we find is that participants start off about the same level in all conditions. In the active case, over time, they significantly learn or use more head movement, but in the fixed and active condition, they use very little, and these are on the order of, say, 0.5 centimeter to 1 or 1.5 centimeters.
Yeah, thank you.
Mm-hmm.
Is this live? No, it's not.
Oh.
All right. Well, I'd like to thank the speaker. We'll go into